Hi everyone, so today we're going to be looking at nitrogen and fertilizers. So let's first see the structure of nitrogen gas. So nitrogen molecule is N2, so which means that you're going to have two atoms of nitrogen bonded together. It is a non-metal, therefore it's going to form covalent bonding. It is in group 5, which means that it has valency 3. This means that it's going to form only 3 covalent bonds. So we can have 3 covalent bonds. So each nitrogen will form 3 covalent bonds. Each of these bonds means that there is a dot and a cross. So from this we can draw the dot and cross diagram. So each of these means a dot and a cross. So we have 3 lines. So we're going to have 3 dots and 3 cross. So 3 pairs of dot and cross. And because nitrogen is in group 5, which means that nitrogen will have 5 outermost electrons. So you're going to have 5 dots and 5 crosses. So when we count, we have 1, 2, 3 dots. So we need to add 2 more. And we have 1, 2, 3 crosses. So we need to add 4 and 5. So this is the covalent bonding of nitrogen gas. Now, nitrogen is diatomic, and this triple bond is very strong, which means that it's very hard to break this triple bond, and a very large amount of energy is required to break these triple bonds. This is why nitrogen is unreactive, and it's used to preserve food because it's not going to react with the food. Now, nitrogen is a very important substance used to make ammonia. And ammonia is very important because it makes fertilizers. Now, for the making of ammonia, we're going to see a special kind of reaction, which is called reversible reactions. So there's 2 types of reaction: irreversible reactions that we've seen before. So irreversible reaction, you're going to see arrows like this. And irreversible reaction means that once the reaction is over, so you cannot go back to the starting point. So it's going to proceed in only one direction. So for example, if you have acid reacting with the base, once the reaction is over, you cannot get back the acid or the base. So it proceeds in only one direction, the forward direction. But we have another kind of reaction, which is called reversible reaction. We're going to see arrows like this. Please don't draw arrows like this. Nope. So it has to be half arrow on top and half arrow at the bottom. And reversible reactions, they can take place in both forward and backward direction. And for example, if you have ammonia reacting with acid, ammonia is a weak base. So the reaction is a reversible reaction, means that you can reverse the reaction. So once you have ammonium chloride, this is NH4Cl. Once you have ammonium chloride, the ammonium chloride can also decompose and give back ammonia and hydrochloric acid. So it takes place in both directions. And it will not go to completion, which means that you're never going to have 100% of ammonium chloride. You'll never have this. So you'll always have a certain percentage of both reactants and products. So for example, you could end up with 70% of ammonium chloride and then 30% of reactants, right? And the amount of reactants and products can be changed. So this percentage, I can change this. I can modify conditions, for example, temperature and pressure. If I alter specific conditions, I can change the percentage of products. So I can bring that up to 80%, for example, and bring that down to 20% by playing with these conditions, right? But eventually, I'm never going to get 100% of products. I'll always have some amount of reactants. So we're going to be using special conditions to bring up the amount of products in reversible reactions. So let's see how we make ammonia industrially. This is important. There's two kinds of processes to make ammonia. There's industrial process and lab process. Let's see the industrial process first. So ammonia is NH3. Remember, ammonium, this is a radical, and this is ammonium is a longer word, so it has more hydrogen. Ammonia is a shorter word, it has less hydrogen, NH3. And ammonia contains nitrogen and it contains hydrogen. So we're going to use these as the starting materials. So we get nitrogen from the fractional distillation of liquid air. We've gone through this before. So we're going to cool the air and then we're going to do fractional distillation of the liquefied air, the liquid air, until we get nitrogen that distills off, right? And we get hydrogen from the process of cracking. We're going to see this process in more details when we cover organic chemistry. So nitrogen and hydrogen are going to be used to make ammonia. So this is a map that explains the process, right? So we get nitrogen and hydrogen together. We purify and dry, so we'll remove any impurities, and we'll dry out, so we'll remove water to ensure that there is no H2O in the mixture. And then we're going to use the pressure, 250 atmosphere, 450 degrees Celsius, and finely divided iron catalyst. These conditions are used to maximize amount of ammonia that we get, because it's a reversible reaction. And in the catalytic chamber, this is where you have this reaction that takes place. Nitrogen reacting with hydrogen in a reversible reaction, giving ammonia. And all of them are gases. And once you get the ammonia, we're going to condense it and liquefy it. And any unreacted nitrogen and hydrogen, because remember, it's a reversible reaction, so you're always going to have unreacted products, it's going to go back again in the catalytic chamber. So it's going to be recycled again and again. And this reaction will proceed both in the forward and backward direction. And it releases heat to the surroundings. It's exothermic. And it takes place at high temperature and high pressure. And we use the finely divided iron catalyst to ensure that the reaction is speeded up. So we speed up the reaction. The catalyst is not going to be used up in the reaction. Right, so this is the industrial process to make ammonia. This is called the Haber process. What you will need to know for IGCSE exams, you will need to remember the conditions, temperature, pressure, and catalyst. Very important. And you need to be able to write this chemical equation.